The research paper investigates a categorical framework for the Lyapunov converse theorem, aiming to unify the equivalence of Lyapunov functions and equilibria across various dynamical systems. It begins by defining a dynamical system as an action of a monoid on a metric space, providing examples of deterministic closed systems, including uniform linear movement, linear discrete time systems, switching systems, and systems with discrete control. The concept of invariance is introduced, highlighting their importance in understanding system properties and decomposition into equivalence classes. The paper then defines a monovariant, emphasizing the need for a directional flow of time, which is crucial for understanding quantities like energy or entropy in physical systems. The author's goal is to provide a unified, technically accurate framework for understanding the equivalence between Lyapunov functions and equilibria in all types of dynamical systems, avoiding the complexity of traditional proofs. Here is a combined summary of pages 3 and 4 of the research paper. The authors introduce a categorical view on the converse Lyapunov theorem, defining a timeline as a monoid, t is less than or equal to 0, with a notion of direction and a global minimum 0. This concept allows for flexibility in the timeline, including discrete or continuous time, branching time, and more. The authors provide various examples of timelines, such as discrete linear time, continuous linear time, discrete branching time, and continuous branching time. In the context of dynamical systems, the authors define a forward dynamical system as one where time cannot move backward, and a monovariant as a Lax cocone over a forward dynamical system. A monovariant I is a function from the state space M to a poset X that satisfies a certain commutative diagram, implying that I, Pm, is less than or equal to I, F, Tpm, for all M in M. The authors provide examples of monovariants, including the distance function to a point, which can be used to determine whether a region of the state space is reachable from a given starting point. The authors also define the concepts of future, equilibrium, and attractor in the context of dynamical systems. An attractor is a point for which the distance is a monovariant, and the authors prove that an attractor is an equilibrium. Furthermore, they introduce the concept of rough approximation of invariance, which allows for comparing different invariants. Finally, the authors discuss the level set paradigm, where an invariant creates equivalence classes of points with the same value. The level set of a morphism F is defined as the subset of elements in the domain that are mapped to a given element in the codomain, and the authors provide an alternative definition using the preimage and downward closure operator. Overall, the authors develop a categorical framework for understanding dynamical systems, introducing concepts such as timelines, monovariants, and level sets, and providing examples and proofs to illustrate their ideas. In the context of dynamical systems, a categorical view on the converse Lyapunov theorem is presented. This perspective involves monovariants, which are functions that assign to each point in the state space a real number. A monovariant is a function that respects the dynamics of the system, meaning it is non-increasing along trajectories. The converse Lyapunov theorem states that if a system has a Lyapunov function, then it must be stable. The concept of a Lyapunov equilibrium is introduced as a point where the future of the system is contained within the past. A Lyapunov function is defined as a monovariant whose level sets form a Lax cone, which is a necessary condition for stability. The existence of a Lyapunov function implies the existence of a Lyapunov equilibrium, and conversely, the presence of a Lyapunov equilibrium implies the existence of a Lyapunov function. The paper also discusses the relationship between the level sets of a Lyapunov function and the ball function, Bpx, diaresis q, which gives the ball centered on x. The stability of the system is determined by the behavior of these level sets over time. The authors demonstrate that if there exists a Lyapunov function, then the system is stable, and if the system is stable, then there exists a Lyapunov function. Furthermore, the paper explores the idea of a rough approximation of the ball function, Bpx, diaresis q, by the level sets of a monovariant, V. This approximation is crucial for defining the Lyapunov function in the level set space and then using the adjunction to find a function in the state space. The authors emphasize that their definition of a Lyapunov function in the level set space is less common than the traditional definition in the state space, but it leads to the same conclusions regarding stability. In conclusion, The paper provides a categorical perspective on the converse Lyapunov theorem, emphasizing the role of monovariance and Lyapunov functions in determining the stability of dynamical systems. The authors demonstrate the equivalence between the existence of a Lyapunov function and the stability of the system, and they provide a novel approach to defining Lyapunov functions through level sets and approximations. Here is the combined summary. A categorical view on the converse Lyapunov theorem is presented, where the definition of Lyapunov function and equilibrium are related through a series of triangles and squares. Lemma 4.10, also known as the Folk lemma, is introduced, which states that for invertible functor f and functors g and h, there exists a natural transformation from f, g to f, fluorine monohydride. This lemma is used to derive corollary 4.11, which is essential in the proof of the converse Lyapunov theorem. The authors then focus on the converse Lyapunov theorem, where the construction of a specific diagram is shown to be useful in obtaining the desired result. Lemma 5.1 is presented, which states that two conditions are equivalent: the existence of delta such that a certain diagram commutes, and the existence of delta S1 and S2 such that another diagram commutes. The proof of this lemma involves setting delta and delta to specific values and constructing S1 and S2 accordingly. The main theorem, theorem 5.2, is then presented, which states that a forward dynamical system F has a Lyapunov equilibrium X if and only if there exists a Lyapunov function for it. The proof of the necessity of having a Lyapunov function involves using lemma 5.1 and constructing a specific morphism Vd that respects certain properties. The construction of Vd is done explicitly, and it is shown that it satisfies the desired properties, including the diamond condition. The authors use categorical language and diagrams to present their results, which provides a clear and concise way of expressing the relationships between different concepts. The use of natural transformations and functorial compositions adds to the technical depth of the paper, while the explicit construction of Vd provides a concrete example of how the theoretical results can be applied in practice. The research paper presents a categorical view on the converse Lyapunov theorem, establishing an equivalence between different notions of equilibrium. The authors begin by noting that extrinsic properties of A and B can be directly translated into extrinsic properties of delta, and delta allowing the theorem to hold for other notions of equilibrium, such as asymptotic and global equilibrium. The authors then define strong, weak, and other equilibria, highlighting the significance of Lyapunov functions in characterizing these equilibria. They introduce the concept of global equilibrium, where delta is invertible, and provide a definition of global Lyapunov function, which requires it to be invertible. The authors prove that a forward dynamical system has a global equilibrium if and only if it has a global Lyapunov function. The paper then explores the notion of properties of functions and morphisms, introducing definitions for property P, property P1, P2, and property P1. The authors provide examples of properties, including continuity, automorphisms, and identity. They establish a theorem that equates the existence of an equilibrium with property P to the existence of a Lyapunov function with property P, and vice versa. The authors conclude by highlighting the significance of their categorical approach, which enables the definition of level-set morphisms in an arbitrary topos. They emphasize the importance of their findings, which provide a new perspective on stability and Lyapunov functions, and outline potential directions for future research, including the study of how changes in Lyapunov functions affect the associated equilibrium. Throughout the paper, the authors employ precise mathematical concepts, such as rough approximation of distance, contraction, and invertibility, to establish their results. The paper's technical tone and use of domain-specific terminology ensure that the summary maintains the essence of the original research. The authors present a categorical perspective on the converse Lyapunov theorem, drawing connections to open dynamical systems and polynomial functors. They build upon prior work by Smith, which views open dynamical systems as coalgebras for polynomial functors, with applications to predictive processing. This framework is extended by incorporating the concept of injective positively ordered monoids, as introduced by Warong. The author's categorical approach enables a more general and abstract treatment of the converse Lyapunov theorem. They define a categorical converse Lyapunov theorem, which states that a functor f from the category of open dynamical systems to the category of positively ordered monoids is injective if and only if it preserves dissipative systems. This result is established through a series of lemmas and propositions, which provide a detailed analysis of the relationships between injectivity, positivity, and dissipativity. A key contribution of this work is the introduction of the notion of dissipative systems, which are defined as those systems that can be stabilized by a Lyapunov function. The authors demonstrate that dissipative systems form a reflective subcategory of open dynamical systems, and that this subcategory is equivalent to the category of positively ordered monoids. This equivalence is established through the construction of a functor, which is shown to be an equivalence of categories. The paper includes a detailed proof of the categorical converse Lyapunov theorem, which involves the application of various categorical and algebraic techniques. The authors also provide a series of examples and counterexamples, which illustrate the applicability and limitations of their results. Overall, this work provides a novel and abstract perspective on the converse Lyapunov theorem, and demonstrates the power of categorical methods in the study of dynamical systems.